Hi everyone, let's continue. So first, let's talk about norm. A vector norm on Rn is a function from Rn to R with the following properties. First, the norm of all the vectors is greater or equal to 0. Okay? Second, the norm is 0 if and only if the vector is the 0 vector. Okay, sorry, I should put a arrow on top of the 0. So this is a 0 vector. Third, the norm of scalar multiple, let's say alpha times the vector x, equals the absolute value of alpha times the norm of x. Okay, for all the alpha is a real numbers and x is a vector in Rn. Fourth, we satisfy the triangular inequality. So the norm of x plus y is less than equal to the norm of x plus the norm of y. Why we call it triangular inequality? Well, think about it. If we have x and this is y, well then this guy, so this is x, this is y, then this guy is x plus y, right? And look at the norm. We have the sum of the two sides is greater or equal to the other side, right? So this is a triangular inequality. Okay, and vector norm. So vector norm, which is the magnitude of a vector, okay? So here we have the following norms. First one, we have the L1 norm. So L1 norm is defined to be the absolute value of all the coordinates, and then we add them all up. Okay, so that's the sum of the absolute values of all the coordinates. And the L2 norm, which is the Euclidean norm, that is the square root of all the coordinates square. And we usually use this one. Okay, do you remember in linear algebra or calculus 3 when we talk about vectors and we talk about the length of vectors, we use this Euclidean norm. Okay, and we also have the L infinity norm. Okay, so this is the maximums within the absolute values of all the coordinates. So far, so good, everybody. So this is the definition. And you can see, you can actually prove them all of these definitions. They are norms, okay? They are all greater or equal to 0, and they're 0 if and only if the vector is the 0 vector. And when we have constant multiple, we can pull it outside of the norm, but we multiply by absolute value of that constant multiple. Okay, and it also satisfies the triangular inequality. So far, so good, everybody. Let's look at example 3. So we want to find all the norms for the vector x, which is -2, 1, and -3. Okay, first, let's look at the L1 norm. The L1 norm is the absolute value of each coordinate, and then add them all up. Absolute value of -2 is 2. Absolute value of 1 is 1. Absolute value of -3 is 3. So when we add them all up, we get 6. So that is the L1 norm. So far, so good, everybody. Okay, next. How about the L2 norm? L2 norm is the square root of each coordinate square. Right? What's -2 square? That's 4. 1 square is 1. 3 square is 9. So we get square roots of 14. So far, so good, everybody. And the L infinity norm is the maximum of the set of, we look at the absolute value of each coordinates. Absolute value of -2 is 2, absolute value of 1 is 1, absolute value of -3 is 3. What's the maximum number in this set? Ooh, that is 3. So far, so good, everybody. And these are the L1 norm of a vector, L2 norm of a vector, and L infinity norm of a vector. Alright, so let's continue. Okay, so we just talked about the vector norm. Right now, let's define matrix norm. So a matrix norm is subordinate to a vector norm. It is defined as, so that we have a matrix A. The matrix norm equals the supremum, okay, the supremum of the norm of the vector A applied on X, right? This is a vector. And over the norm of the X vector. Okay, so supremum is like the maximum. All right. Okay, what does this mean? Okay, this means I think about all vector in Rn. Okay, we let A, the matrix A, add on this vector. Okay, and usually A is an m by m matrix. And here X is a vector in Rn. Okay, then AX is also a vector in Rn, right? So we consider all the norm of the vectors AX, and we use it to divide it by the norm of X. Okay, and we get a lot of numbers because each direction in which each X vector gives us a value. Okay, and we want to find the maximum of those values. So to help you to understand the difference between maximum and supremum, let me write it down here. Okay, so maximum is the largest number of the set. Okay, and supremum is the smallest upper bound of the set. Let me give you some example. Okay, let's consider the set 1, 2, 3, 4. Well, then the maximum is 4, and the supremum is also 4. Okay? Because 4 is the largest number, and 4 is also an upper bound of this set. All the elements in this set less than equal to this upper bound. Okay? I can give you one more example here. Consider the infinite, so the infinite list of numbers, 1/2, 2/3, 3/4. So it's like n over n plus 1. So far, so good, everybody? And here we have infinite many numbers, right? And you know n over n plus 1. This is the same as n plus 1 minus 1 over n plus 1. So that is 1 minus 1 over n plus 1. So when n is getting bigger, well, this guy is getting close to 1, right? It's smaller than 1, right? All of them are smaller than 1, not equal, but it's getting closer to 1. So in this case, you can see we don't have a maximum because we don't have a largest number in this set. This number is increasing all the time. So we don't have a maximum, but we do have a supremum. The supremum is 1. Okay, 1 is the upper bound of this set, and it is the smallest upper bound of this set. So any number in this set is less than equal to that supremum, the upper bound. So far, so good. So I hope this example can help you to understand the difference between maximum and supremum. Okay. Next, let me use a different color here. Okay, so it's the supremum of the norm of the vector ax over the norm of x. And actually, instead of looking at all vectors in Rn, it is enough to look at the unit vectors in Rn. Why is that? Oh, think about it. So given any given vector x, we can think about its unit vector in that direction. Well, that is x over the norm of x, right? And now ax over the norm of x. Well, this is the same as we can divide it by 1 over x there. Here we can also divide it by 1 over x. The norm of x. Now what do we get? We can move the norm of x inside, so we have a times this guy. Okay. Oh, I need to move this. Oh, okay. Okay. Let me move this unit vector here. This is the unit vector. Okay, and the bottom you can see is just 1. So that's why this guy, any vector x, is the same as the norm of a times a unit vector in that direction. So that's why we get this equal. So far, so good, everybody? Okay, but in general, we won't use this definition to compute because there are infinitely many vectors, infinitely many unit vectors in Rn. How can we compute all of them and find the supremum for all those vectors, right? All those magnitudes. Okay, so the following are the actual ways to compute the matrix norms. Okay, what we just went over is just the definition of a matrix norm. Okay, all right. So do you remember vector norm? We have the L1 norm, L2 norm, and the L infinity norm. But for matrix norm, we actually have 4. Okay, so we will discuss 4 norms. Okay, first the L1 norm. L1 norm for the matrix is the maximum of the column sum. What's column sum? So we have a matrix, right? Column sum is you have the sum of the absolute value of the entries in a column. Okay, that is one number, and we want to find the maximums of those numbers. So far, so good, everybody? So J, we have the jth column. So this is jth column. And for the jth column, when you add them up, the entries are A1J, A2J, and ANJ. Okay? And what is L2 norm? Well, L2 norm is actually the square root of the lambda mass. So lambda mass is the largest eigenvalues of the matrix A Hermitian transpose. So you know what is transpose, right? Transpose is like the rows and columns like interchange, right? You just interchange them like a mirror image about the diagonal, and then we interchange those entries, right? That is transpose. Well, the Hermitian transpose is actually, so let me put it down. Hermitian transpose is the complex conjugate of the transpose of A. Alright, so in general, if we have complex numbers, then we take the transpose of A, and then for each ng, we replace by its complex conjugates. Okay, but if A is a real matrix, okay, the entries are real numbers, then the Hermitian transpose is just the transpose. So far, so good, everybody. So lambda max is the largest eigenvalues of the matrix A transpose times A. Yeah, in general, this is harder to compute. Okay. And we have the L infinity norm. So L infinity norm is the maximum of the column sum. So it's very easy to get confused with the L1 norm and L infinity norm. So L infinity norm is the maximum of the row sum. So for each row, you add up all the absolute values of the entries together, and then you pick the largest number among those values. Okay, so L1 norm is maximum of column sum. L infinity norm is the maximum of the row sum. Yeah, so be careful with that L1 norm and L infinity norm. Don't get confused. Next, we have the Euclidean norm. It's also called Frobenius norm. And how do we calculate? This is very similar as before when we calculate the vector norm, the L2 norm for the vector. It is the square roots, and then we add up all the entries square. Okay, and so this is the Euclidean norm. So for the vector norm, L2 norm and Euclidean norm, they are the same thing. They're both square roots of the each entry square. Okay, but for matrix, the L2 norm and the Euclidean norm, they separate. So Euclidean norm is like the previous definition, but L2 norm is the square root of lambda max. Lambda max is the eigenvalues, largest eigenvalues of the matrix A transpose times A. Okay, I know that's a lot. Let's do some example can help us to understand, right? Let's compute all the norms for the matrix A. Alright, so let me change my orange color. Okay, so how do we compute L1 norm? Well, L1 norm, that is the maximum column sum, right? So that's the maximum of, look at the first column, 6 plus 3. Look at the second column. We're talking about absolute value of the entries. So 4 plus 1. So far, so good. And this is the same as maximum between 9 and 5. And we get 9. By the way, if we have a set of finite numbers, okay, so the numbers of elements in the set is finite, the maximum is actually the same as supremum. So far, so good, everybody? Yeah, because we can find the largest elements in the set because it's finite. Alright, let's continue. Let's calculate L1 norm and then L infinity norm and then Euclidean norm. Last, we find the L2 norm because the L2 norm is the hardest one. Okay, so L infinity norm is the maximum row sum. So that's the maximum. Well, the rows, this guy and this guy. And when we talk about row sum, we mean the sum of the absolute value of the entries in that row, right? So we have maximum of 10 and 4. Well, that is 10. So far, so good, everybody. And then we have the Euclidean norm. Okay, Euclidean norm equals square roots each entry square. So 6 square, 4 square, 3 square, 1 square. And I don't need to put a negative there because negative 1 square is just plus 1. Right? So we have 36, 16, 3 squares 9, and then 1. This is 10. This is 26. 26 plus 36 is 62. So far, so good, everybody. Okay, what is 6 square root of 62? let's calculate it so that it's easier for us to compare. Alright, so we have square root of 62, 7.87401. 7.87401. So far, so good, everybody? Okay, now let's compute the L2 norm. First, we need to compute the matrix A transpose A. And what is that? Well, A transpose, the diagonal elements stay the same, and then we switch them, right? So -4 now is here, 3 is there. Times A is the same thing. Okay. And how do we calculate matrix multiplication? We use row times column. So 6 times 6, 36. 3 times 3, 9. Right? And then we use the first row times the second column. 6 times -4, -24. 3 times -1, -3. Right? And then we use second row times the first column. -4 times 6 -24. -1 times 3 is -3. Then last second row times second column. -4 times -4 is 16. -1 times -1 is 1. So we get 45 -27 -27 and 17. So far, so good, everybody? So this is the matrix A transpose times A, right? Next, we want to find the largest eigenvalues for this matrix. Do you still remember how to compute eigenvalues? So we first compute the determinants of, so let's call this is B. So we compute the determinants of B minus lambda I. What's B minus lambda I? It means for the diagonal elements, we subtract lambda. And then the rest stay the same. So determinant of a 2x2 matrix is cross multiply, but we subtract. So 45 minus lambda times 17 minus lambda, subtract -21 times -27, and then times -27. Okay, what is that? Well, let's see. 45 times 17 minus 45 lambda minus 17 lambda plus lambda squared, and then this is negative, 3 negative is negative 27 squared. Okay, let's see. Let's reorder it. So lambda squared, and then 45 plus 17 is 62. Right? And then we have 45 times 17 minus 27 squared. What is that? Oops, wrong one. I need my calculator right here. 45 times 17 minus 27 squared. 36. Okay, so this is the characteristic equation. Right? We set it equals 0. Do you still remember that? Yes? Then the eigenvalue is the root of this characteristic equation. Okay, so what is lambda? In general, the number are not so nice that we can factor it. So let's use the quadratic formula. 2a, a is 1, and then negative b is 62, plus or minus b squared, 62 squared, minus 4ac. 4 times 36. Okay, what is that? Okay, so 62, oops, wrong one. 62, what did I do? Uh-oh. Here, 62 squared minus 4 times 36. And see? 3700. So when you take square roots, you see that 100 square root of 100 is 10. So 10 is square root of 37 over 2. Or we can divide it by 2. Then we have 31 plus or minus 5 square root of 37. Okay, see? We have 2 by 2 matrix. Then we will have 2 eigenvalue. We pick the larger one, right? The larger one is the positive one. So L2 norm of A is the square root of the lambda mass. Lambda mass is 31 plus 5 square roots of 37, right? Okay, what is this number? Calculator, where are you? Here. So, oops. We do square root of 31 plus 5 square root of 37. See? The answer is 7.83669. 7.83669, and then what? 6539. 6539. So far, so good, everybody? Okay, so this is our L2 norm. Now you can see L1 norm, L infinity norm, Euclidean norm, they're easier to compute. But for the L2 norm, because we need to find the eigenvalue of the matrix A transpose A. So in general, it's hard to find it. Okay, for 2 by 2 matrix, this is a way we can do it, because we will get a quadratic equation. We can always solve a quadratic equation by the quadratic formula. But if A is a 3 by 3 matrix, well, then we have a polynomial of degree 3. If we have some rational roots, we might use the rational root theorem. But if the roots are not rational, what do? How do you find the roots? Aha! We just learned in chapter 2. Do you remember? We can graph the function plus some points and graph it, and then we can use intermediate value theorem and mean value theorem to see like to guess how many roots it has, and then we can use bisection method, regular Fossey method, secant method, Newton's method to approximate the roots as close as we want. That is what we do in general. And after we find 3 eigenvalues, okay, then we pick the largest one. Okay, we pick the largest one and we take the square root of that. That is gonna be our L2 norm for the matrix. Okay, all right, let's continue. Oh, okay. So before we get into the next topic to talk about condition of a matrix, I want to show you how to use MATLAB or Octave to compute norms. Okay, so how to find norms of this vector? Well, the syntax is we just put norm x comma 1. So this is the L1 norm. Okay, so this is the L1 norm. And then this is the L2 norm. It's also the Euclidean norm for a vector. So for vector, Euclidean norm and L2 norm, they're the same thing. And this is the L infinite norm. Okay, so this is just what we input, and then we can see the norms. So far, so good, everybody? Okay, and for a matrix, so for a matrix, L1 norm is like norm matrix A, comma 1. L2 norm is norm A, 2, comma 2, okay? L infinity norm is norm A and then comma infinity. We use INF, okay? But for the Euclidean norm, usually we use this notation, E. Okay, then we use norm A, and then we use this apostrophe, okay, for obedience, because it's also called Frobenius norm. Okay, so that is the Euclidean norm. So we input the matrix, and then we plot those norms, then we can get the answer. See, in this MATLAB, we input the matrix, and then when we compute L1 norm, we get a number, L2 norm, we get another number, L infinity norm, get this number, and the Euclidean norm give us these numbers. So far, so good, everybody? Okay, so this is how to use MATLAB to compute. Right now, I want to check our answer with you, because we just compute 2 examples. Why don't we check our answers and see whether it works? Okay, so let's first check the vectors. Okay, so here, where is our MATLAB or Octave? Right here. So let's see. Let me shrink a little bit. Wait, okay, so alright. Okay, so this is the vector x equals let's do -2, 1, -3. Oh, by the way, we need column vector for x. Okay, so it has to be a column vector, and then the L1 norm, because we can consider vector is like a special case of the matrix, right? And then L1 norm is the maximum of column sum. So if we have column vector, then the L1 norm is like the sum of the coordinates, absolute value of the coordinates, right? And then the L infinity norm is the maximum between different coordinates. Okay, so we have a column vector, and then we can do norm of x, comma 1. See, we get 6. And let's do norm x2, 3.7417. And what is that? We can actually compute, because here we have square root of 14. Let's see, what is this syntax? Yeah, so square root of 14 is, we get the same number. Okay, and norm of x infinity, so INF, we get 3. Do we get 3? Yes. See, our answer match. So just remember, when you want to compute a vector norm, you want to input a column vector. You don't want to input a row vector. Okay, if you input a row vector, then the L1 norm and L infinity norm will flip. Okay, how about a matrix? So let's plug in this matrix A. 6 minus 4, 3 minus 1. Okay, and norm A, L1 norm of A is 9. Yeah, that match with our results. And L infinity norm of A, 10. Ooh, that match our results. Okay, how about L2 norm? Sorry, this is a Euclidean norm, not L2 norm. So we do Frobenius. Is it FRO or FROB? Okay, FRO, yes. So close it, enter. 7.8740. Yeah, that match, right? Okay, and how about L2 norm? Well, L2 norm is norm A, comma 2. 7.8367. Yes, see, that also match our results. So in this video, we talk about norms, and we talk about vector norms and matrix norms. Vector, we have 3 norms: L1 norm, our infinite norm. The L2 norm is the same as the Euclidean norm. But however, for matrix, the L2 norm and the Euclidean norms, they're different things. And L1 norm is the maximum column sum. L infinity norm is the maximum of the row sum. Euclidean norm is the square root of the sum of all the entries squared. And then the L2 norm is the hardest one. We need to compute the matrix A transpose times A and then find the eigenvalues of this matrix. Pick the largest one, okay? And then take square root of that. So far, so good, everybody? Okay, so in next class, we will talk about condition numbers. See you soon. Bye.